Hi everyone, welcome back. So today what we're going to do is we're going to move on from our discussion on dipole antennas to another topic. So this is so the idea here is that we don't want to cover every single antenna. That would take forever in this class. It's not really a dedicated antennas class, but rather we want to cover broad concepts that essentially explain a wide variety of antennas, right? So in that spirit, we are going to start by today discussing what is known as Babinet's theorem. It's also sometimes known as Babinet's principle. And this will allow us to study a wide class of antennas called complementary antennas. And one example or one subclass of that are frequency independent antennas. Okay, so we would like to actually develop the proof of Babinet's theorem in this class, not just state it, because the proof itself is interesting and it uses a lot of the concepts that we've developed in the past. Okay, so the proof is kind of long. It requires several preliminary results that we need to develop, which we'll call as lemmas. So these are like small theorems, I guess. So the first one is this. Okay, so let's say I have some surface current. Uh, there is some current on some surface. So let's say I'm on an XY plane. So this is the XY plane, and there is some current distribution on the surface, J. Then we want to show that the tangential field on this surface, magnetic field, everywhere is zero. Everywhere except the places where you have current. So if you have current in this region, then sort of in this region, the tangential magnetic field goes to zero. That's what we want to establish. Okay. So I'll say H tangential in the plane containing J surface is equal to zero. Okay, so let's prove this. Okay, given that I have J surface, I can find the magnetic vector potential as mu integral J of r prime, J of r comma r prime, ds prime. And where G is e to the ik r minus r prime over 4 pi r minus r prime. Right? And we'll see this later. This is called the Green's function, but we've already seen this equation before, right? So this is the Green's function. So you've seen this expression before, right? We saw it in arbitrary, when you have an arbitrary time dependence, and we also saw it in terms of in the context of time harmonic weights, right? So you're familiar with that. Yeah, once I have A, you can find H. Right? It's 1 over mu curl of A, which is surface integral times the curl of J of r prime times G r comma r prime ds. Right? And this curl applies to the whole thing, this whole thing. And we know that J is only a function of r prime, whereas the curl operation is over the r component. Right? So the curl only applies to G. So you have J times curl of G, and then you can use a vector identity to rewrite that as gradient of G cross J. Okay? R prime. All right, so we can compute the gradient of G because we know what G is already. That would be ik minus 1 over r minus r prime e to the ik mod r minus r prime divided by modulus of r minus r prime square times r minus r prime. Okay. So that's what the gradient of G is. Okay, so when we substitute this gradient back in here, right, essentially all of this is a coefficient. The vector quantity is defined by r minus r prime, right? And we're interested only in the surface that contains the charge density or the current density, right? The surface current density. So r lies in the same plane, r prime obviously lies in the same plane, and j also lies in the same plane, right? Which means that essentially when I take a cross product of this and this, it would be taking a cross product of two vectors that lie in that plane, which means that that cross product has to be normal to that plane, right? So it implies that h r is perpendicular to the surface S. Okay, where our S surface is this surface, the xy plane, that example. And then of course this means that H tangential is 0 on S. Okay? All right. So we've proven the first lemma. The second result we need is the dual of this, that E tangential due to a magnetic surface current is 0 on the same S that contains the surface current. Okay, and of course this is basically you can prove this either from scratch again or you can prove it using duality. That you apply duality to the previous problem and that gives you this problem, so it's the same proof. So that's about that. Okay, the next result we need to develop is called the complementary theorem. And this is an important result that we'll use to prove Babinet's theorem. Okay, so what is this saying? So essentially the problem statement has three cases. So I'm going to draw them. Case one, there's an electric current. There is some sheet of metal, PEC sheet, with some holes cut in it. That's one hole, that's another hole. So I'm just going to color this in. Okay. So for now, we'll assume this PEC is in the XY plane. The currents are in Z less than 0. And we're looking at fields on Z greater than 0, E1, H1. Okay. So this is Z greater than 0. Right, so you have some current distribution in Z less than 0. You have a PEC sheet with some holes on the XY plane. And in the right half space, which is Z greater than 0, you have some fields. Okay, so that's the first situation. The second situation is where I have the same currents. Copy this. Same currents. But now, actually zoom out a little bit. But now, wherever I had the apertures or the holes, I place PMC. Okay, and then I don't have PEC anywhere. So it's just gap, holes everywhere, or free space everywhere, except wherever I had the apertures, I have PMC now. Okay, and in this problem, I have again fields on the right. E2, H2, Z is greater than 0. This is again the XY plane. Okay, in the third case, I have again the same current. And now I have no sheets anywhere. XY plane is all empty. And I have fields on the right. And these fields I'll call as the incident fields. Okay, because these are the fields where you have no scatterers. These are the incident fields, EI, HI. Okay, so those are the three different situations. And the complementary theorem says that, write it in a new page. Okay, the complementary theorem says that EI is E1 plus E2 and hi is h1 plus h2. Okay. So essentially you have free space that gives you hi. You put some PMC sheets that gives you E2H2. You take the complementary problem where you replace PMC with aperture and you replace apertures with PEC, and that gives you E1H1. And these three fields satisfy this relationship. That's what the complementary theorem is saying. Okay, so we want to prove this. So let's go ahead and do that. Okay, so we'll label some surfaces. So I label this surface as S1, which is the shaded region, and this is S2. Yeah, we can label S2 over here. So this is our S2. So S2 is the surface which contains the PMC region, and S1 was the surface that had the PEC region. So in this case, this would also be S2. So we're just talking about the area, we're not talking about the material here. And then S1 would be this, the rest of it. This is all S1. Okay. So we know on S1, right, because it's PEC, the fields have to satisfy boundary condition. In the first problem, fields in the first problem were E1, H1, and they have to satisfy the boundary condition on the PEC, which is on S1, which is that these are 0. Similarly, on S2, PMC have to satisfy boundary condition, and those fields are E2, H2. They need to be 0. Okay. All right, so that's the first step. The second step is that in case A, HI, so the incident field, let's go back here. Okay, so this current here radiates some field, right, which is the incoming field or the incident field. That field excites some currents on this PEC everywhere, right? Those currents produce no tangential component of H on this and this aperture. And that's what we proved in the lemma 1, right? Which means that the only tangential component, so okay, let me do that again. So I said that the currents on this PEC don't generate any H, tangential H on this aperture and this aperture. Okay, which means that the tangential H on this aperture and this aperture have to be from the incident field, HI. Right, so HI comes in, that produces some tangential field, and no tangential field can come from the surface currents, which means that the only tangential field out here is from the incident field. And that's what we are saying. So HI produces JS on S1. Which produces no, it's tangential on S2. It implies that n hat cross H1 is equal to n hat cross Hi. The tangential component of H1 and Hi on S2 are equal. Okay. Similarly, in case B, n hat cross E1 is equal to n hat cross EI on S1. Right? Okay. So now if you look at this, on S1 we have n hat cross E1 equal to n hat cross EI, and n hat cross E1, this should be E2, sorry. We have n hat cross E2 equal to n hat cross EI, and n hat cross E1 is 0. Right, so we can add them up. Implies on S1, n hat cross E1 plus E2 equal to n hat cross EI. Okay, and similarly, n hat cross H1 plus H2 is equal to n hat cross HI. Okay. All right. So if you go back here to this problem, and this is the kind of the tricky part of the argument. Okay, E1 and H1 are in the right half space, which is free space, right? E2 and H2 also are in the right half space, which is free space. Now, E1 and H1 satisfy source-free Maxwell's equations on the right half space. E2, H2 satisfy source-free Maxwell's equations on the right half space. And EI, HI also satisfy source-free Maxwell's equations on the right half space. Okay. Now, for the right half space, the boundary is the xy plane and a hemisphere at infinity, which we've shown in the past has no contribution. So we can ignore that. So the boundary for the right half space is nothing but the xy plane, right? Which is S1 plus S2, which means that what? From uniqueness, if we have two solutions that have the same boundary fields, we know that the interior field needs to be the same. So if you have two solutions to Maxwell's equations that agree on a given boundary, then the fields inside need to be the same. And in fact, that's a little bit stronger than what the condition is. The condition is that if you have two solutions, one of them where the E field agrees on one part of the space and the H field agrees on the complementary part of that of the boundary. So if the E field agrees on one part of the boundary and the H field agrees on the complementary part of the boundary, then that's enough for uniqueness to be applied. Right? And that's exactly what we have here. We have two solutions to Maxwell's equations, E1 plus E2. Of course, linear combination of solutions should be also a solution. Right? So we have E1 plus E2, comma H1 plus H2 as one solution. We have EI, comma HI as another solution. Right? The boundary on S1, E is agreeing. On S2, which is the complementary boundary, we have H agreeing, which means that these satisfy the conditions for uniqueness. Right? Implies from uniqueness, E1 plus E2 is equal to EI and H1 plus H2 is equal to HI. This is only in the right half space. Okay, and that completes the proof. Okay, so maybe you need to stare at that proof a couple more times to really sink in, but that's the entirety of the proof. Okay, so now given that we have this complementary theorem, we want to establish Babinet's theorem. So what does Babinet's theorem say? Again, we have two problems. So I have a current source and I have of a similar PEC with some apertures inside it. Okay. And now on the right hand side, I have two fields, E1, which I will write as E1E. We'll see what that is, which is a combination of the incident field and the scattered field. Similarly, H1 is a combination of the incident field and the scattered field. Okay, so the incident field is the field when I don't have PEC, right? I don't have PEC, J directly comes out here, produces fields everywhere. E1 and H1 are the fields in the right half space when I do have a scatterer. And the scattered fields are nothing but E1 minus EI and H1 minus HI. That's how the scattered field is defined. It's the difference between the incident field and the total field. Okay, or the total field and the incident field. That's what the scattered field is. So this is again the XY plane. And this is z greater than 0. Okay, that's the first problem statement. The second one is I have some sources, same distribution, but now I'm using magnetic current sources. So this is different than the complementary theorem, right? Complementary theorem had electric currents. Now we're using a magnetic current distribution. Same distribution, but we just flip it to a magnetic current. And here we still have PEC. But now instead of PEC everywhere, and then some apertures, the apertures have PEC, and there's free space everywhere else in the XY plane. This is also different than the complementary theorem, right, where we had PMC instead of PEC. So this is the XY plane. And then on the right-hand side, we have fields. And now I'm labeling it as M. And here now you see why this was labeled as E, because we had an electric current source on the left. Now we have a magnetic current source, so this should give me an M. That's the idea. Right, that's equal to EIM plus ESM. Again, same idea. Incident field and scattered field. And H2M is HIM plus HSM. Okay? All right. So Babinet's theorem says that E1 is equal to minus square root of mu over epsilon HSM, and H1 is equal to square root of epsilon over mu ESM. All right, so what is this saying? So this is saying that if I have these two problems, I solve them, I find these total fields. Maybe I should label this as E. Yes. Okay. And it's saying that this E1E is equal to a scaled version of, E1E is a scaled version of HSM. And H1E is a scaled version of ESM. Okay. So the total field on one case is related to the scattered fields in the other case. We need to establish that relationship. All right. So let's prove this. Okay, so we start with A. So first step, start with situation A and apply complementary theorem to it. Okay, so what happens to that? So if I apply complementary theorem to A, then I have same currents, I have my PMC, and I have E2, H2. Right? I'll call this E2E, H2E. Okay, because they're produced by an electric current. All right. Then I can write the results of complementary theorem was that E1E plus E2E are equal to EIE. And then H1E plus H2E is equal to HIE. Okay? Then we apply duality to this. So you see that the duals of this would become JM, these would become PEC, and that's nothing but what this is, right? So we start from here, we apply complementary theorem, then we apply duality, and that gives us this. That's the trick. Okay, so how do you apply duality to this? If you go back here, so we said that if you apply duality, this, maybe I should use this. So this would become exactly equal to case B, this case, right? This case, which means that this field solution is exactly the dual of this field solution. And that's what duality means. You have to apply it to the sources, to the scatterers, and the fields. Right? So when I do that, What does that mean? What is the duality relationship between those two fields? E2E is dual with square root of mu over epsilon H2M, right? But that is equal to nothing but square root of mu over epsilon HIM plus HSM, right? And then similarly, H2E goes to square root of minus square root of epsilon over mu E2M, which is equal to square root minus square root of epsilon over mu EIM plus ESM. Okay? Okay. Okay, so when we take duality, which means we're finding the dual of this, we want to find the duals of this. We also need to find the duals of the incident fields, right? Because we're changing the source as well. When we change the source, the fields radiated by the source are the incident fields. Those also need to be taken as, those also need to be, we need to apply duality to them as well. So how do they satisfy duality? E1 goes to square root of mu over epsilon HIM, and that would be for the magnetic source, and HIE would go to minus square root of epsilon over mu EIM, right? That would be the dual of the incident fields. Now you take all of these equations and you substitute them, take these, substitute them into that, right? And that will give us exactly what we want. So you can substitute and look and simplify. It's just one step of algebra, which I'm skipping. That gives us this. Okay, that completes the proof. All right, so the proof is kind of an interesting review of several concepts like uniqueness and then duality and things like that. But we really want to use the proof and see what kind of engineering can we do with it, right? This is sort of an applied course. It's called Applied Electromagnetic Theory. So I don't know, it's theory and applied, I guess. But let's see. So one of the big applications of Babinet's theorem is this thing called complementary antennas. Okay, so what's the idea? The idea is that I start with, let's say, a dipole antenna, planar dipole. Looks something like this. Let me actually try that again. And let's assume it's fed by parallel plate line or parallel transmission lines, two-wire transmission line. Right, so this is all PC. Okay. And the dual of this, let me actually move this to the side. The dual to this would then be transmission line like that. And then everything is metal, right? This is all metal. So this is going to take me a second. So all of this is metal. And the same goes for out here. This is all metal. Right? So these are duals of each other. And this is called a slot antenna. I should say they are complementary to each other rather than duals. Okay. And this is, of course, your familiar dipole antenna. And they are planar. Both of them are planar, right? So, of course, wherever there was PEC, I put gap, and wherever there's air, I put PEC. Okay. We want to see how are the input impedances of these antennas related. Okay, so let's say I excite one of them with an electric current source, small electric current source, and you can show that you can excite a slot antenna with an equivalent magnetic current source. So in reality, it's not a magnetic current source. In reality, it's something that you can represent as a magnetic current source. It's a small magnetic current source. Okay, so given these excitations, we want to find what is the relationship between their input impedances. Okay, so to find the input impedance, I need to know what is the terminal voltage and the terminal current. Right, so to find the terminal voltage, I can integrate over this loop, half loop. That gives me the terminal voltage across this, and I can find the terminal current by integrating around this half loop. Okay, so we'll see that this is, let's say I label this as AB, these points as CD, and I can do the same thing on this side. So I can integrate this to find the current. So this will give me the current that's going through this, and this will give me the voltage across this. So this gives me this voltage, and this gives me this current. Similarly, here I can find the current going through this by integrating across over this bridge, sort of a half loop around this bridge from point A to B, and you see that the points A to B are the same. Okay, and then the voltage across this line can be, you can get from integrating from here to here, from C to D. Okay, so let's do that explicitly. I'm saying in the dipole case, VD is given as integral A to B E1 dot dl, where E1 is the electric field of the first problem, right, if you remember. And then ID is minus 2 times integral C to D H1 dot dl. Right, and the factor of 2 is there because this is only a half loop integral, whereas you need a closed loop integral to give you the total current. So you only get half the current from this integral from C to D, and it's equal to the other half because from symmetry, right? Since it's symmetric along Z, a half loop is enough. Similarly, on this side, we have Vs equal to integral C to D Em dot dl. You can write this as E1E, H1E, E2M dot dl, and Is is 2 times integral A to B H2M dot dl. Okay, and there should be a minus here as well. Okay, so these are the relationships, right? Now I can apply Babinet's theorem to these guys. Okay, that would give me Vd is equal to minus eta integral A to B this should be a plus, sorry, because it depends on the direction of current flow, right? Because I guess current flows this way and then flows back like this. Clarify that a little bit more. Let's do this again. So I need to erase this current a little bit and redraw it. Maybe it's a little bit careless over there. Okay. So what's happening here is that when I have this current source like this, excitation, in this arm the current would flow up, and in this arm the current would flow down. Okay. And you can kind of show that, of course, it kind of makes sense that these currents need to be continuous like that, right? So if you integrate C to D from here, that gives you current flowing this way. But your current in reality is flowing this way. So if this is ID, right, then the integral needs a negative sign because they're in the opposite directions. Right? So this is your ID. Whereas in this case, maybe draw this. So we draw this part. Okay, so I have this bridge right here. I have this. Okay, we draw this as well. Okay. So in this case, the current in the center line flows this way. Okay, so when the current is flowing like this, then integral A to B is in the right direction of ID. So in this case, ID is like this. Because the magnetic currents flow like this, and the electric field is pointed inward. Okay? Is it inward or outward? Let me check my notes quickly. Yeah, inward. So the electric fields are pointed inward. Okay, so that's why you have a plus on one and the negative on the other one. Okay, so you go back, you apply Babinet's theorem to this, and this gives you minus eta integral A to B HSM dot dl, and ID is equal to minus 2 over eta integral C to D ESM dot dl. Okay. All right. So now you can kind of see where this is going. So we see that this is related to this. This is somehow related to this. Right. So if I take ZD, that's nothing but VD over ID. That's eta square over 2 times integral A to B HM dot dl HSM dot dl divided by integral C to D ESM dot dl. Okay, and now we make an approximation, which is that this small magnetic current does not produce any incident field that is out here. Okay, so it kind of decays by the time it gets there. Of course, because you have the scatterer, this current can generate a field along this transmission line, and that can propagate. Right? And there's no loss there, assuming this is kind of metallic PC, pure PC. But the incident field is in free space. So if I have a small current in free space, then that field decays pretty quickly, right, as we move away. So we can assume that at the terminals of the antenna, the impact of that is basically negligible. Okay, then we can say HS is equal to H2 and ES is equal to E2. Right, so this is approximately equal to eta square over 2 integral A to B H2 M dl, and the bottom would become integral C to D E2 M dl dot dl, and that's nothing but Vs over Is. Vs over Is over 2 actually, right? Or Vs over, yeah, Is divided by 2. Right, so this is nothing but 2Zs, okay? Where Zs is for the slot. So that implies that Zd Zs is equal to eta square over 4. Okay, and during this derivation, we never really use the fact that the dipole is shaped a certain way and the slot is shaped a certain way. You can take any antenna that's planar, take its complementary, you can find effectively the right contour integrals to find the voltage and current. And for any antenna, you can essentially, for any planar antenna like this, which is PEC, you can find the same relationship. Okay, since we made no assumption about the actual shape of the antenna. Okay, which means that ZA and ZC, where I have an antenna, I take its complementary antenna, the product of their input impedances would always be eta square over 4. This is a very, very, very important, practical, useful relationship. Okay? So what are the implications of this, right? Remember that eta is a constant. Right? Since eta is a constant, when ZA increases or as a function of frequency, ZC should decrease as a function of frequency. And that's the reason you'll see that we've covered folded dipoles before. In the long 6.5 hour video, we did folded dipole and folded slot. And even in the class, in the homeworks, you'll see folded dipole and folded slot. So essentially, we'll see that folded dipole increases the impedance of a dipole antenna by a factor of 4. Because of Babinet's theorem, folded slot, the impedance should decrease by a factor of 4. Okay. Similarly, dipole has an impedance of 73 ohms or so, or 70 ohms, around 70 ohms, which means that a slot antenna should have 377 square divided by 4 divided by 73, right? Whatever that value is, I don't remember, but you can find that. Okay, another very important consequence of this is frequency independent antennas. Yeah, broadband antennas, you can think of them as. So what does that mean? So if I make an antenna which is self-complementary, okay, if it's self-complementary, then its impedance, so I'll call it self-complementary antenna. Its impedance must be 8 over 2, 377 over 2, which is what, 290 or so, right? 289 ohms. 289? No, 189 ohms. Yeah, 189 ohms. So essentially, you can make an antenna that has a very, very broadband performance because eta, of course, is frequency independent, which means that Z would also be frequency independent, right? Okay, so what kind of antennas am I talking about? We can do a few examples here. So one example is a bow tie antenna. Looks something like this. And maybe this is not a very good self-complementary structure. So it has to be, it's better. Something like that. This is PEC, right? So the self-complementary part of it would have an antenna like that. And of course, it's not the same orientation, but from the point of view of the port, which is down here, it looks like the same antenna, right? So that's why bow tie dipoles have very high bandwidth. Okay, I can make a small gap here in order to excite it there, like this. Then I place my excitation across this. Okay. Another set of antennas are spiral antennas. One port like that, the other port like that. So it doesn't look very self-complementary, but of course, if you add some thickness to this, then it becomes self-complementary, as long as the thickness and the gap are the same. Right? And there are different kinds of spirals. There's like Archimedean spiral, there is, planar spiral, and so on and so forth. And they all are self-complementary. There's also a weird looking spiral called a sinuous antenna. right? Which also has a similar self-complementary structure. Okay, and you can make your own. I mean, you can make an arbitrary kind. So for example, one example is that, I can make some shape like that and a copy of this. Yeah, it's going to take forever. Let me give you a quick example. So I can make a bulb like that. And I take the same bulb, make a copy on the bottom. And the top side, I make it metallic. Bottom side, I make the rest of it metallic, right? Like all of this is metal now, right? So this is called top-loaded dipole. And that's another example. And so you can put an excitation across this like that. Okay. Now, of course, in reality, these are not infinite bandwidth, and the bandwidth is limited on the higher end. So the upper part of the bandwidth is limited by this gap, and this gap. And the lower part of the bandwidth is limited by at what point you truncate it. Truncate here, then you have, a lower end of the bandwidth will be more. If you truncate here, it will be a bit less. Right? In the same way, it's the length of these arms that you make. And in this case, it's you truncate this sheet, right? At some point. So you eventually have kind of a band limited structure, but they can be very broadband. So you can get like several octaves of bandwidth out of these guys. Okay. There are other ways to analyze bow tie and spiral and so on, but this is one way to look at them. Okay, now one of the big drawbacks of this kind of Babinet's theorem in these kind of antennas is that they are planar, right? Which means that they radiate in two directions, both up and down. So if these are in the XY plane, then they radiate both in positive Z and negative Z. And that's not always desirable. In many cases, you don't want to radiate. So in the quote unquote back side, you don't want to have any back radiation. So you want to put a ground plane. But once you put a ground plane, then it becomes a 3D structure. Once you have a 3D structure, the Babinet's theorem we developed here doesn't really apply anymore, right? So in those cases, you need to think about broadband techniques from a different point of view, and we'll do that. So in the next class, we'll look at other broadband techniques, other bandwidth enhancement techniques that don't rely on just planar structures. Okay, so we'll probably stop here. It's a good place to stop. Just to review, we essentially did a long proof of Babinet's theorem. Then we looked at what complementary antennas are. And we also looked at the end, what self-complementary antennas and essentially frequency independent antennas are. One more thing I want to mention is that Babinet only guarantees broad bandwidth in terms of impedance bandwidth, right? The impedance is broad over the entire band. Not all self-complementary structures are equally good. Like for example, this top-loaded dipole on the right side, right, like this one, this is not really very symmetric in some sense, right? So over different parts of the bandwidth, the radiation pattern can change quite a bit. Uh, whereas the spiral is quite a symmetric structure. So over different parts of the band, different regions of the spiral radiate. So maybe this diameter, this part radiates at the higher frequencies, whereas at the lower frequencies, the outer arms radiate. But they are all kind of circular in shape, right? So you can get very consistent radiation pattern over the entire band. And again, this kind of dipole is also somewhat decent in terms of radiation pattern. But then again, if you have a sinuous antenna or a spiral antenna, you don't get linear polarization that easily. It's usually circularly polarized, whereas these dipoles can give you linear polarization and so on. So there are many other considerations than just the bandwidth. And of course, Babinet just tells you about the impedance bandwidth. It doesn't give you any guarantees of good radiation performance or the good radiation characteristics over the entire band. And so all of that need to also be taken into account when you're doing antenna design. So I just wanted to mention that. Okay, with that, we'll stop here. If you have any questions, you can leave them in the comments below or let me know. If not, thank you. I'll see you in the next one.